In the Snake River Valley the latest lavas are much younger. Their surfaces are so fresh and undecayed that here the effusive eruptions may well have continued to within the period of human history. Low lava domes like those of Iceland mark where last the basalt outwelled and spread far and wide before it chilled, Fig 341. In places small mounds of scoria show that the eruptions were accompanied to a slight degree by explosions of steam. So fluid was the superheated lava that recent flows have been traced for more than 50 miles. The rocks underlying the Columbia lavas, where exposed to view, are seen to be cut by numerous great dikes of dense basalt, which marked the fissures through which the molten rock rose to the surface. The Tertiary included times of widespread and intense volcanic action in other continents as well as in North America. In Europe, Vesuvius, p. 231, and Etna began their career as submarine volcanoes in connection with earth movements which finally lifted Pliocene deposits in Sicily to their present height 4,000 feet above the sea. Volcanoes broke forth in central France and southern Germany, in Hungary, and the Carpathians. Innumerable fissures opened in the crust from the north of Ireland and the western islands of Scotland to the Faroes, Iceland, and even to Arctic Greenland, and here great plateaus were built of flows of basalt similar to that of the Columbia River. In India, at the opening of the Tertiary, there had been an outwelling of basalt, flooding to a depth of thousands of feet 200,000 square miles of the northwestern part of the peninsula, Fig 342, and similar inundations of lava occurred where are now the tablelands of Abyssinia. From the Middle Tertiary on, Asia Minor, Arabia, and Persia were the scenes of volcanic action. In Palestine the rise of the uplands of Judea at the close of the Eocene, and the downfaulting of the Jordan Valley, p. 221, were followed by volcanic outbursts. In comparison with the Middle Tertiary, the present is a time of volcanic inactivity and repose. Fig 342. Map showing the lava sheet, shaded area, of western India. Erosion of tertiary mountains and plateaus. The mountains and plateaus built at various times during the Tertiary and at its commencement have been profoundly carved by erosive agents. The Sierra Nevada mountains have been dissected on the western slope by such canyons as those of Kings River and the Yosemite. 6 miles of strata have been denuded from parts of the Wasatch Mountains since their rise at the beginning of the era. From the Colorado Plateaus, whose uplift dates from the same time, there have been stripped off 10,000 feet of strata over thousands of square miles, and the colossal canyon of the Colorado has been cut after this great denudation had been mostly accomplished, Fig 130. On the eastern side of the continent, as we have seen, a broad peneplain had been developed by the close of the Cretaceous. The remnants of this old erosion surface are now found upwarp to various heights in different portions of its area. In southern New England it now stands 1,500 feet above the sea in western Massachusetts, declining then southward and eastward to sea level at the coast. In southwestern Virginia it has been lifted to 4,000 feet above the sea. Manifestly this upwarp occurred since the peneplain was formed, it is later than the Mesozoic, and the vast dissection which the peneplain has suffered since its uplift must belong to the successive cycles of Cenozoic time. Revived by the uplift, the streams of the area trenched it as deeply as its elevation permitted, and reaching grade, opened up wide valleys and new peneplains in the softer rocks. The Connecticut Valley is tertiary in age, and in the weak Triassic sandstones, p. 370, has been widened in places to 15 miles. Dating from the same time are the valleys of the Hudson, the Susquehanna, the Delaware, the Potomac, and the Shenandoah. In Pennsylvania and the states lying to the south the Mesozoic peneplain lies along the summits of the mountain ridges. On the surface of this ancient plain, tertiary erosion etched out the beautifully regular pattern of the Allegheny mountain ridges and their intervening valleys. The weaker strata of the long, regular folds were eroded into longitudinal valleys, while the hard Paleozoic sandstones, such as the Medina, p. 335, and the Pocono, p. 350, were left in relief as bold mountain walls whose even crests rise to the common level of the ancient plain. From Virginia far into Alabama the great Appalachian Valley was open to a width in places of 50 miles and more, along a belt of intensely folded and faulted strata where once was the heart of the Appalachian Mountains. In Figure 70, the summit of the Cumberland Plateau, marks the level of the Mesozoic peneplain, while the lower erosion levels are tertiary and quaternary in age. Fig 343. Diagram of the Allegheny Mountains, Pennsylvania from Davis Elementary Physical Geography. Life of the Tertiary Period. Vegetation and climate. The highest plants in structure, the dicotyls, such as are deciduous forest trees, and the monocotyls, represented by the palms, were introduced during the Cretaceous. The vegetable kingdom reached its culmination before the animal kingdom, and if the dividing line between the Mesozoic and the Cenozoic were drawn according to the progress of plant life, the Cretaceous instead of the Tertiary would be made the opening period of the modern era. The plants of the Tertiary belonged, for the most part, to genera now living, but their distribution was very different from that of the flora of today. In the earlier Tertiary, palms flourished over northern Europe, and in the northwestern United States grew the magnolia and laurel, along with the walnut, oak, and elm. Even in northern Greenland and in Spitsbergen there were lakes covered with water lilies and surrounded by forests of maples, poplars, limes, the cypress of our southern states, and noble sequoias similar to the big trees and redwoods of California. A warm climate like that of the Mesozoic, therefore, prevailed over North America and Europe, extending far toward the pole. In the later Tertiary the climate gradually became cooler. Palms disappeared from Europe, and everywhere the aspect of forests and open lands became more like that of today. Grasses became abundant, furnishing a new food for herbivorous animals. Animal life of the Tertiary. Little needs to be said of the Tertiary invertebrates, so nearly were they like the invertebrates of the present. Even in the Eocene, about 5% of marine shells were of species still living, and in the Pliocene the proportion had risen to more than one-half. Fishes were of modern types. Teleosts were now abundant. The ocean teemed with sharks, some of them being voracious monsters 75 feet and even more in length, with a gape of jaw of 6 feet, as estimated by the size of their enormous sharp-edged teeth. Snakes are found for the first time in the early Tertiary. These limbless reptiles, evolved by degeneration from lizard-like ancestors, appeared in non-poisonous types scarcely to be distinguished from those of the present day. Mammals of the early Tertiary. The fossils of continental deposits of the earliest Eocene show that a marked advance had now been made in the evolution of the mammalia. The higher mammals had appeared, and henceforth the lower mammals, the monotremes and the marsupials, are reduced to a subordinate place. Fig 344. Phenocodus. These first true mammals were archaic and generalized in structure. Their feet were of the primitive type, with 5 toes of about equal length. They were also plantigrades, that is, they touched the ground with the sole of the entire foot from toe to heel. No foot had yet become adapted to swift running by a decrease in the number of digits and by lifting the heel and sole so that only the toes touch the ground, a tread called digitigrade. Nor was there yet any foot like that of the cats, with sharp retractile claws adapted to seizing and tearing the prey. The forearm and the lower leg each had still 2 separate bones, ulna and radius, fibula and tibia, neither pair having been replaced with a single strong bone, as in the leg of the horse. The teeth also were primitive in type and of full number. The complex heavy grinders of the horse and elephant, the sharp cutting teeth of the carnivores, and the cropping teeth of the grass-eaters were all still to come. Phenocodus is a characteristic genus of the early Eocene, whose species varied in size from that of a bulldog to that of an animal a little larger than a sheep. Its feet were primitive, and their 5 toes bore nails intermediate in form between a claw and a hoof. The archaic type of teeth indicates that the animal was omnivorous in diet. A cast of the brain cavity shows that, like its associates of the time, its brain was extremely small and nearly smooth, having little more than traces of convolutions. The long ages of the Eocene and the following epochs of the Tertiary were times of comparatively rapid evolution among the Mammalia. The earliest forms evolved along diverging lines toward the various specialized types of hoofed mammals, rodents, carnivores, proboscideans, the primates, and the other mammalian orders as we know them now. We must describe the tertiary mammals very briefly, tracing the lines of descent of only a few of the more familiar mammals of the present. The horse. The pedigree of the horse runs back into the early Eocene through many genera and species to a 5-toed, 3 short-legged ancestor little bigger than a cat. Its descendants gradually increased in stature and became better and better adapted to swift running to escape their foes. The leg became longer, and only the tip of the toes struck the ground. The middle toe, digit number 3, originally the longest of the 5, steadily enlarged, while the remaining digits dwindled and disappeared. The inner digit, corresponding to the great toe and thumb, was the first to go. Next, number 5, the little finger, was also dropped. By the end of the Eocene a 3-toed genus of the horse family had appeared, as large as a sheep. The hoof of digit number 3 now supported most of the weight, but the slender hoofs of digits 2 and 4 were still serviceable. In the Miocene the stature of the ancestors of the horse increased to that of a pony. The feet were still 3-toed, but the side hoofs were now mere toe-claws and scarcely touched the ground. The evolution of the family was completed in the Pliocene. The middle toe was enlarged still more, the side toes were dropped, and the palm and foot bones which supported them were reduced to splints. 3 or, more accurately, with 4 perfect toes and a rudimentary 5th corresponding to the thumb. Fig 345. Development of forefoot, a. the forearm, b. the molar, c. of the horse family. While these changes were in progress the radius and ulna of the forelimb became consolidated to a single bone, and in the hind limb the fibula dwindled to a splint, while the tibia was correspondingly enlarged. The molars, also gradually lengthened, and became more and more complex on their grinding surface. The neck became longer, the brain steadily increased in size and its convolutions became more abundant. The evolution of the horse has made for greater fleetness and intelligence. The rhinoceros and tapir. These animals, which are grouped with the horse among the odd-toed, perissodactyl, mammals, are now verging toward extinction. In the rhinoceros, evolution seems to have taken the opposite course from that of the horse. As the animal increased in size it became more clumsy, its limbs became shorter and more massive, and, perhaps because of its great weight, the number of digits were not reduced below the number 3. Like other large herbivores, the rhinoceros, too slow to escape its enemies by flight, learned to withstand them. It developed as its means of defense a nasal horn. Peculiar offshoots of the line appeared at various times in the Tertiary. A rhinoceros, semi-aquatic in habits, with curved tusks, resembling in aspect the hippopotamus, lived along the water courses of the plains east of the Rockies, and its bones are now found by the thousands in the Miocene of Kansas. Another developed along a line parallel to that of the horse, and herds of these light-limbed and swift-footed running rhinoceroses ranged the Great Plains from the Dakotas southward. Fig 346. A tertiary mastodon. The tapirs are an ancient family which has changed but little since it separated from the other perissodactyl stocks in the early tertiary. At present, tapirs are found only in South America and Southern Asia, a remarkable distribution which we could not explain were it not that the geological record shows that during tertiary times tapirs ranged throughout the northern hemisphere, making their way to South America late in that period. During the Pleistocene they became extinct over all the intervening lands between the widely separated regions where now they live. The geographic distribution of animals, as well as their relationships and origins, can be understood only through a study of their geological history. Fig 347. Head of Dino. They're the proboscideans. This unique order of hoofed mammals, of which the elephant is the sole survivor, has been traced back to the close of the Eocene. In the middle and later tertiary it was represented by huge creatures so nearly akin to the mastodons of the Pleistocene that they are often included in that genus. The tertiary mastodon was furnished with a long, flexible proboscis, and armed with two pairs of long, straight ivory tusks, the pair of the lower jaw being smaller. The dino. There was a curious offshoot of the line, which developed in the Miocene in Europe. In this immense proboscidean, whose skull was 3 feet long, the upper pair of tusks had disappeared, and those of the lower jaw were bent down with a backward curve in walrus fashion. Fig 348. Crown of mastodon tooth. Fig 349. Tooth of an extinct elephant, the mammoth in the true elephants, which do not appear until near the close of the tertiary. The lower jaw loses its tusks and the grinding teeth become exceedingly complex in structure. The grinding teeth of the mastodon had long roots and low crowns crossed by 4 or 5 peaked enameled ridges. In the teeth of the true elephants the crown has become deep, and the ridges of enamel have changed to numerous upright, plate-like folds, their interspaces filled with cement. The two genera mastodon and elephant are connected by species whose teeth are intermediate in pattern. The proboscideans culminated in the Pliocene, when some of the giant elephants reached a height of 14 feet. Fig 350. Evolution of the artiodactyl foot, illustrated by existing families: A. Pig, B. Roebuck, C. Sheep, D. Camel. The artiodactyls comprise the hoofed mammalia which have an even number of toes, such as cattle, sheep, and swine. Like the perissodactyls, they are descended from the primitive 5-toed plantigrade mammals of the lowest Eocene. In their evolution, digit number 1 was first dropped, and the middle pair became larger and more massive, while the side digits, numbers 2 and 5, became shorter, weaker, and less serviceable. The 4-toed artiodactyls culminated in the tertiary. At present they are represented only by the hippopotamus and the hog. Along the main line of the evolution of the artiodactyls the side toes, digits 2 and 5, disappeared, leaving as proof that they once existed the corresponding bones of palm and sole as splints. The 2-toed artiodactyls, such as the camels, deer, cattle, and sheep, are now the leading types of the herbivores. Swine and peccaries are 2 branches of a common stock, the first developing in the Old World and the second in the New. In the Miocene a noticeable offshoot of the line was a gigantic pig-like brute, a root-eater, with a skull a yard in length, whose remains are now found in Colorado and South Dakota. Camels and llamas. The line of camels and llamas developed in North America, where the successive changes from an early Eocene ancestor, no larger than a rabbit, are traced step by step to the present forms, as clearly as is the evolution of the horse. In the late Miocene some of the ancestral forms migrated to the Old World by way of a land connection where Bering Strait now is, and there gave rise to the camels and dromedaries. Others migrated into South America, which had now been connected with our own continent, and these developed into the llamas and guanacos, while those of the race which remained in North America became extinct during the Pleistocene. Some peculiar branches of the camel stem appeared in North America. In the Pliocene arose a llama with the long neck and limbs of a giraffe, whose food was cropped from the leaves and branches of trees. Far more generalized in structure was the oreadon, an animal related to the camels, but with distinct affinities also with other lines, such as those of the hog and deer. These curious creatures were much like the peccary in appearance, except for their long tails. In the Middle Eocene they roamed in vast herds from Oregon to Kansas and Nebraska. The ruminants. This division of the artiodactyls includes antelopes, deer, oxen, bison, sheep, and goats, all of which belong to a common stock which took its rise in Europe in the Upper Eocene from ancestral forms akin to those of the camels. In the Miocene the evolution of the two-toed artiodactyl foot was well nigh completed. Bone-like growths appeared on the head, and the two groups of the ruminants became specialized: the deer with bony antlers, shed and renewed each year, and the ruminants with hollow horns, whose two bony knobs upon the skull are covered with permanent, pointed, horny sheaths. The ruminants evolved in the Old World, and it was not until the later Miocene that the ancestors of the antelope and of some deer found their way to North America. Mountain sheep and goats, the bison, and most of the deer, did not arrive until after the close of the Tertiary, and sheep and oxen were introduced by man. The hoofed mammals of the Tertiary included many offshoots from the main lines which we have traced. Among them were a number of genera of clumsy, ponderous brutes, some almost elephantine in their bulk. The carnivores. The ancestral lines of the families of the flesh-eaters, such as the cats, lions, tigers, etc., the bears, the hyenas, and the dogs, including wolves and foxes, converge in the creodonts of the early Eocene, an order so generalized that it had affinities not only with the carnivores but also with the insect-eaters, the marsupials, and the hoofed mammals as well. From these primitive flesh-eaters, with small and simple brains, numerous small teeth, and plantigrade tread, the different families of the carnivores of the present have slowly evolved. Dogs and bears. The dog family diverged from the creodonts late in the Eocene, and divided into two branches, one of which evolved the wolves and the other the foxes. An offshoot gave rise to the family of the bears, and so closely do these two families, now wide apart, approach as we trace them back in Tertiary times that the Amphicean, a genus dog-like in its teeth and bear-like in other structures, is referred by some to the dog and by others to the bear family. The well-known plantigrade tread of bears is a primitive characteristic which has survived from their creodont ancestry. Cats. The family of the cats, the most highly specialized of all the carnivores, divided in the Tertiary into two main branches. 1. The saber-toothed tigers, Fig 351, which takes its name from their long, saber-like, sharp-edged upper canine teeth, evolved a succession of genera and species, among them some of the most destructive beasts of prey which ever scourged the earth. They were masters of the entire northern hemisphere during the Middle Tertiary, but in Europe during the Pliocene they declined, from unknown causes, and gave place to the other branch of cats which includes the lions, tigers, and leopards. In the Americas the saber-toothed tigers long survived the epoch. Fig 351. Saber-toothed tiger. Marine mammals. The carnivorous mammals of the sea, whales, seals, walruses, etc., seem to have been derived from some of the creodonts of the early Tertiary by adaptation to aquatic life. Whales evolved from some land ancestry at a very early date in the Tertiary. In the marine deposits of the Eocene are found the bones of the Zeuglodon, a whale-like creature 70 feet in length. Primates. This order, which includes lemurs, monkeys, apes, and man, seems to have sprung from a creodont or insectivorous ancestry in the lower Eocene. Lemur-like types, with small, smooth brains, were abundant in the United States in the early Tertiary, but no primates have been found here in the Middle Tertiary and later strata. In Europe, true monkeys were introduced in the Miocene, and were abundant until the close of the Tertiary, when they were driven from the continent by the increasing cold. Advance of the Mammalia during the Tertiary. During the several millions of years comprised in Tertiary time, the mammals evolved from the lowly, simple types which tenanted the earth at the beginning of the period, into the many kinds of highly specialized mammals of the Pleistocene and the present, each with the various structures of the body adapted to its own peculiar mode of life. The swift feet of the horse, the horns of cattle and the antlers of the deer, the lion's claws and teeth, the long incisors of the beaver, the proboscis of the elephant, were all developed in Tertiary times. In especial the brain of the Tertiary mammals constantly grew larger relatively to the size of body, and the higher portion of the brain, the cerebral lobes, increased in size in comparison with the cerebellum. Some of the hoofed mammals now have a brain 8 or 10 times the size of that of their early Tertiary predecessors of equal bulk. Nor can we doubt that along with the increasing size of brain went a corresponding increase in the keenness of the senses, in activity and vigor, and in intelligence. Chapter XXII. The Quaternary. The last period of geological history, the Quaternary, may be said to have begun when all, or nearly all, living species of mollusks and most of the existing mammals had appeared. It is divided into two great epochs. The first, the Pleistocene, or glacial epoch, is marked off from the Tertiary by the occupation of the northern parts of North America and Europe by vast ice sheets. The second, the recent epoch, began with the disappearance of the ice sheets from these continents, and merges into the present time. The Pleistocene epoch. We now come to an episode of unusual interest, so different was it from most of the preceding epochs and from the present, and so largely has it influenced the conditions of man's life. The records of the glacial epoch are so plain and full that we are compelled to believe what otherwise would seem almost incredible, that following the mild climate of the Tertiary came a succession of ages when ice fields, like that of Greenland, shrouded the northern parts of North America and Europe and extended far into temperate latitudes. The drift. Our studies of glaciers have prepared us to decipher and interpret the history of the glacial epoch, as it is recorded in the surface deposits known as the drift. Over most of Canada and the northern states this familiar formation is exposed to view in nearly all cuttings which pass below the surface soil. The drift includes two distinct classes of deposits: the unstratified drift laid down by glacier ice, and the stratified drift spread by glacier waters. The materials of the drift are in any given place in part unlike the rock on which it rests. They cannot be derived from the underlying rock by weathering, but have been brought from elsewhere. Thus, where a region is underlain by sedimentary rocks, as is the drift-covered area from the Hudson River to the Missouri, the drift contains not only fragments of limestone, sandstone, and shale of local derivation, but also pebbles of many igneous and metamorphic rocks, such as granites, gneisses, schists, dike rocks, quartzites, and the quartz of mineral veins, whose nearest source is the Archean area of Canada and the states of our northern border. The drift received its name when it was supposed that the formation had been drifted by floods and icebergs from outside sources, a theory long since abandoned. Fig. 352. Stratified drift overlaying unstratified drift. Massachusetts. The distribution also of the drift points clearly to its peculiar origin. Within the limits of the glaciated area it covers the country without regard to the relief, mantling with its debris not only lowlands and valleys but also highlands and mountain slopes. The boundary of the drift is equally independent of the relief of the land, crossing hills and plains impartially, unlike water-laid deposits, whose margins, unless subsequently deformed, are horizontal. The boundary of the drift is strikingly lobate also, bending outward in broad, convex curves, where there are no natural barriers in the topography of the country to set it such a limit. Under these conditions such a lobate margin cannot belong to deposits of rivers, lakes, or ocean, but is precisely that which would mark the edge of a continental glacier which deployed in broad tongues of ice. The rock surface underlying the drift. Over much of its area the drift rests on firm, fresh rock, showing that both the preglacial mantle of residual waste and the partially decomposed and broken rock beneath it have been swept away. The underlying rock, especially if massive, hard, and of a fine grain, has often been ground down to a smooth surface and rubbed to a polish as perfect as that seen on the rock beside an alpine glacier where the ice has recently melted back. Frequently it has been worn to the smooth, rounded hummocks known as rocs moutonnées, and even rocky hills have been thus smoothed to flowing outlines like rocs moutonnées on a gigantic scale. The rock pavement beneath the drift is also marked by long, straight, parallel scorings, varying in size from deep grooves to fine striae as delicate as the hair lines cut by an engraver's needle. Where the rock is soft or closely jointed it is often shattered to a depth of several feet beneath the drift, while stony clay has been thrust in among the fragments into which the rock is broken. In the presence of these glaciated surfaces we cannot doubt that the area of the drift has been overridden by vast sheets of ice which, in their steady flow, rasped and scored the rock bed beneath by means of the stones with which their basal layers were inset, and in places plucked and shattered it. Till. The unstratified portion of the drift consists chiefly of sheets of dense, stony clay called till, which clearly are the ground moraines of ancient continental glaciers. Till is an unsorted mixture of materials of all sizes, from fine clay and sand, gravel, pebbles, and cobblestones, to large boulders. The stones of the till are of many kinds, some having been plucked from the bedrock of the locality where they are found, and others having been brought from outside and often distant places. Land ice is the only agent known which can spread unstratified material in such extensive sheets. The fine material of the till comes from two different sources. In part it is derived from old residual clays, which in the making had been leached of the lime and other soluble ingredients of the rock from which they weathered. In part it consists of sound rock ground fine, a drop of acid on fresh, clayey till often proves by brisk effervescence that the till contains much undecayed limestone flour. The ice sheet, therefore, both scraped up the mantle of long weathered waste which covered the country before its coming, and also ground heavily upon the sound rock underneath, and crushed and wore to rock flour the fragments which it carried. The color of unweathered till depends on that of the materials of which it is composed. Where red sandstones have contributed largely to its making, as over the Triassic sandstones of the eastern states and the Algonquian sandstones about Lake Superior, the drift is reddish. When derived in part from coaly shales, as over many outcrops of the Pennsylvanian, it may when moist be almost black. Fresh till is normally a dull gray or bluish, so largely is it made up of the grindings of unoxidized rocks of these common colors. Except where composed chiefly of sand or coarser stuff, unweathered till is often exceedingly dense. Can you suggest by what means it has been thus compacted? Did the ice fields of the glacial epoch bear heavy surface moraines like the medial and lateral moraines of valley glaciers? Where was the greater part of the load of these ice fields carried, judging from what you know of the glaciers of Greenland? Boulders of the drift. The pebbles and boulders of the drift are in part stream gravels, boulders of weathering, and other coarse rock waste picked up from the surface of the country by the advancing ice, and in part are fragments plucked from ledges of sound rock after the mantle of waste had been removed. Many of the stones of the till are dressed as only glacier ice can do, their sharp edges have been blunted and their sides faceted and scored. Fig 353. At Drumlin, Wisconsin we may easily find all stages of this process represented among the pebbles of the till. Some are little worn, even on their edges, some are planed and scored on one side only, while some in their long journey have been ground down to many facets and have lost much of their original bulk. Evidently the ice played fast and loose with the stone carried in its basal layers, now holding it fast and rubbing it against the rock beneath, now loosening its grasp and allowing the stone to turn. Boulders of the drift are sometimes found on higher ground than their parent ledges. Thus boulders have been left on the sides of Mount Katahdin, Maine, which were plucked from limestone ledges 12 miles distant and 3,000 feet lower than their resting place. In other cases stones have been carried over mountain ranges, as in Vermont, where pebbles of Burlington red sandstone were dragged over the Green Mountains, 3,000 feet in height, and left in the Connecticut Valley 60 miles away. No other geological agent than glacier ice could do this work. The boulders of the drift are often large. Boulders 10 and 20 feet in diameter are not uncommon, and some are known whose diameter exceeds 50 feet. As a rule, the average size of boulders decreases with increasing distance from their sources. Why? Till plains. The surface of the drift, where left in its initial state, also displays clear proof of its glacial origin. Over large areas it is spread in level plains of till, perhaps boulder-dotted, similar to the plains of stony clay left in Spitsbergen by the recent retreat of some of the glaciers of that island. In places the unstratified drift is heaped in hills of various kinds, which we will now describe. Fig 354. Map of a portion of a drumlin area near Oswego, New York. Drumlins. Drumlins are smooth, rounded hills composed of till, elliptical in base, and having their longer axes parallel to the movement of the ice as shown by glacial scorings. They crowd certain districts in central New York and in southern Wisconsin, where they may be counted by the thousands. Among the numerous drumlins about Boston is historic Bunker Hill. Drumlins are made of ground moraine. They were accumulated and given shape beneath the overriding ice, much as are sandbars in a river, or in some instances were carved, like rocks moutonnées, by an ice sheet out of the till left by an earlier ice invasion. Terminal moraines. The glaciated area is crossed by belts of thickened drift, often a mile or two, and sometimes even 10 miles and more, in breadth, which lie transverse to the movement of the ice and clearly are the terminal moraines of ancient ice sheets, marking either the limit of their farthest advance or pauses in their general retreat. Fig 355. Terminal moraine, Staten Island. The surface of these moraines is a jumble of elevations and depressions, which vary from low, gentle swells and shallow sags to sharp hills, 100 feet or so in height, and deep, steep-sided hollows. Such tumultuous hills and hummocks, set with depressions of all shapes, which usually are without outlet and are often occupied by marshes, ponds, and lakes, surely cannot be the work of running water. The hills are heaps of drift, lodged beneath the ice edge or piled along its front. The basins were left among the tangle of morainic knolls and ridges, Fig 105, as the margin of the ice moved back and forth. Some bowl-shaped basins were made by the melting of a mass of ice left behind by the retreating glacier and buried in its debris. Fig 356. Esker, New York. The stratified drift. Like modern glaciers, the ice sheets of the Pleistocene were ever being converted into water about their margins. Their limits on the land were the lines where their onward flow was just balanced by melting and evaporation. On the surface of the ice along the marginal zone, rivulets no doubt flowed in summer, and found their way through crevasses to the interior of the glacier or to the ground. Subglacial streams, like those of the Malaspina Glacier, issued from tunnels in the ice, and water ran along the melting ice front as it is seen to do about the glacier tongues of Greenland. All these glacier waters flowed away down the chief drainage channels in swollen rivers loaded with glacial waste. It is not unexpected therefore that there are found, over all the country where the melting ice retreated, deposits made of the same materials as the till, but sorted and stratified by running water. Some of these were deposited behind the ice front in ice-wall channels, some at the edge of the glaciers by issuing streams, and others were spread to long distances in front of the ice edge by glacial waters as they flowed away. Eskers are narrow, winding ridges of stratified sand and gravel whose general course lies parallel with the movement of the glacier. These ridges, though evidently laid by running water, do not follow lines of continuous descent, but may be found to cross river valleys and ascend their sides. Hence the streams by which eskers were laid did not flow unconfined upon the surface of the ground. We may infer that eskers were deposited in the tunnels and ice-walled gorges of glacial streams before they issued from the ice front. Fig. 357. Kames, New York kames are sand and gravel knolls, associated for the most part with terminal moraines, and heaped by glacial waters along the margin of the ice. Fig. 358. Diagram illustrating the formation of kame terraces. Glacier ice, T. Terraces. Kame terraces are hummocky embankments of stratified drift sometimes found in rugged regions along the sides of valleys. In these valleys long tongues of glacier ice lay slowly melting. Glacial waters took their way between the edges of the glaciers and the hillside, and here deposited sand and gravel in rude terraces. Outwash plains are plains of sand and gravel which frequently border terminal moraines on their outward face, and were spread evidently by outwash from the melting ice. Outwash plains are sometimes pitted by bowl-shaped basins where ice blocks were left buried in the sand by the retreating glacier. Valley trains are deposits of stratified drift with which river valleys have been aggraded. Valleys leading outward from the ice front were flooded by glacial waters and were filled often to great depths with trains of stream-swept drift. Since the disappearance of the ice, these glacial floodplains have been dissected by the shrunken rivers of recent times and left on either side the valley in high terraces. Valley trains head in morainic plains, and their material grows finer down valley and coarser toward their sources. Their gradient is commonly greater than that of the present rivers. The extent of the drift. The extent of the drift of North America and its southern limits are best seen in Figure 359. Its area is reckoned at about 4 million square miles. The ice fields which once covered so much of our continent were altogether 10 times as large as the inland ice of Greenland, and about equal to the enormous ice cap which now covers the Antarctic regions. The ice field of Europe was much smaller, measuring about 770,000 square miles. Centers of dispersion. The direction of the movement of the ice is recorded plainly in the scorings of the rock surface, in the shapes of glaciated hills, in the axes of drumlins and eskers, and in trains of boulders, when the ledges from which they were plucked can be discovered. In these ways it has been proved that in North America there were 3 centers where ice gathered to the greatest depth, and from which it flowed in all directions outward. There were thus 3 vast ice fields: one the Cordilleran, which lay upon the Cordilleras of British America, one the Keewatin, which flowed out from the province of Keewatin, west of Hudson Bay, and one the Labrador ice field, whose center of dispersion was on the highlands of the peninsula of Labrador. As shown in Figure 359, the western ice field extended but a short way beyond the eastern foothills of the Rocky Mountains, where perhaps it met the far-traveled ice from the Great Central Field. The Keewatin and the Labrador ice fields flowed farthest toward the south, and in the Mississippi Valley the one reached the mouth of the Missouri and the other nearly to the mouth of the Ohio. In Minnesota and Wisconsin and northward they merged in one vast field. Fig. 359. Hypothetical map of the Pleistocene ice sheets of North America from Salisbury's Glacial Geology of New Jersey. The thickness of the ice was so great that it buried the highest mountains of eastern North America, as is proved by the transported boulders which have been found upon their summits. If the land then stood at its present height above sea level, and if the average slope of the ice were no more than 10 feet to the mile, a slope so gentle that the eye could not detect it, and less than half the slope of the interior of the inland ice of Greenland, the ice plateaus about Hudson Bay must have reached a thickness of at least 10,000 feet. Fig. 360. Hypothetical map of the Pleistocene ice sheet of Europe. In Europe, the Scandinavian plateau was the chief center of dispersion. At the time of greatest glaciation, a continuous field of ice extended from the Ural Mountains to the Atlantic, where, off the coasts of Norway and the British Isles, it met the sea in an unbroken ice wall. On the south it reached to southern England, Belgium, and central Germany, and deployed on the eastern plains in wide lobes over Poland and central Russia, Fig. 360. At the same time, the Alps supported giant glaciers many times the size of the surviving glaciers of today, and a Piedmont glacier covered the plains of northern Switzerland. The thickness of the drift. The drift is far from uniform in thickness. It is comparatively thin and scanty over the Laurentian highlands and the rugged regions of New England, while from southern New York and Ontario westward over the Mississippi Valley, and on the great western plains of Canada, it exceeds an average of 100 feet over wide areas, and in places has 5 and 6 times that thickness. It was to this marginal belt that the ice sheets brought their loads, while northwards, nearer the centers of dispersion, erosion was excessive and deposition slight. Successive ice invasions and their drift sheets. Recent studies of the drift prove that it does not consist of one indivisible formation, but includes a number of distinct drift sheets, each with its own peculiar features. The Pleistocene epoch consisted, therefore, of several glacial stages, during each of which the ice advanced far southward, together with the intervening interglacial stages when, under a milder climate, the ice melted back toward its sources or wholly disappeared. Fig. 361. Diagram illustrating criteria by which different drift sheets are distinguished. The evidences of such interglacial stages, and the means by which the different drift sheets are told apart, are illustrated in Figure 361. Here the country from N to S is wholly covered by drift, but the drift from N to M is so unlike that from M to S that we may believe it the product of a distinct ice invasion and deposited during another and far later glacial stage. The former drift is very young, for its drainage is as yet immature, and there are many lakes and marshes upon its surface. The latter is far older, for its surface has been thoroughly dissected by its streams. The former is but slightly weathered, while the latter is so old that it is deeply reddened by oxidation and is leached of its soluble ingredients such as lime. The younger drift is bordered by a distinct terminal moraine, while the margin of the older drift is not thus marked. Moreover, the two drift sheets are somewhat unlike in composition, and the different proportion of pebbles of the various kinds of rocks which they contain shows that their respective glaciers followed different tracks and gathered their loads from different regions. Again, in places beneath the younger drift there is found the buried land surface of an older drift with old soils, forest grounds, and vegetable deposits, containing the remains of animals and plants, which tell of the climate of the interglacial stage in which they lived. By such differences as these the following drift sheets have been made out in America, and similar subdivisions have been recognized in Europe. 5. The Wisconsin Formation. 4. The Iowan Formation. 3. The Illinoisan Formation. 2. The Kansan Formation. 1. The Pre-Kansan or Jerseyan Formation. The earliest glacial stage is recorded in an exceedingly old drift sheet left in the province of Alberta, Canada, by the Cordilleran ice field, which seems then to have reached its climax. In the United States, Pre-Kansan drift has either been swept away by later ice invasions, or is found buried beneath their ground moraines. The two succeeding stages mark the greatest snowfall of the glacial epoch. In Kansan times the Keewatin ice field slowly grew southward until it reached 1,500 miles from its center of dispersion and extended from the Arctic Ocean to northeastern Kansas. In the Illinoisan stage the Labrador ice field stretched from Hudson Straits nearly to the Ohio River in Illinois, In the Iowan and the Wisconsin, the closing stages of the glacial epoch, the readvancing ice fields fell far short of their former limits in the Mississippi Valley, but in the eastern states the Labrador ice field during Wisconsin times overrode for the most part all earlier deposits, and, covering New England, probably met the ocean in a continuous wall of ice which set its bergs afloat from Massachusetts to northern Labrador. We select for detailed description the Kansan and the Wisconsin formations as representatives, the one of the older and the other of the younger drift sheets. Fig 362. Photograph of relief map of the United States at the time of the Wisconsin ice invasion by the courtesy of E. E. Howell, Washington, D.C. The Kansan Formation. The Kansan drift consists for the most part of a sheet of clayey till carrying smaller boulders than the later drift. Few traces of drumlins, kames, or terminal moraines are found upon the Kansan drift, and where thick enough to mask the pre-existing surface, it seems to have been spread originally in level plains of till. The initial Kansan plain has been worn by running water until there are now left only isolated patches and the narrow strips and crests of the divides, which still rise to the ancient level. The valleys of the larger streams have been opened wide. Their well-developed tributaries have carved nearly the entire plain to valley slopes, figs 50b, and 59. The lakes and marshes which once marked the infancy of the region have long since been effaced. The drift is also deeply weathered. The till, originally blue in color, has been yellowed by oxidation to a depth of 10 and 20 feet and even more, and its surface is sometimes rusted to terracotta red. To a somewhat less depth it has been leached of its lime and other soluble ingredients. In the weathered zone its pebbles, especially where the till is loose in texture, are sometimes so rotted that granites may be crumbled with the fingers. The Kansan drift is therefore old. Fig 363. Plain of Wisconsin drift, Iowa. The Wisconsin Formation. The Wisconsin drift sheet is but little weathered and eroded, and therefore is extremely young. Oxidation has affected it but slightly, and lime and other soluble plant foods remain undissolved even at the grassroots. Its river systems are still in their infancy, Fig 50a. Swamps and peat bogs are abundant on its undrained surface, and to this drift sheet belong the lakelands of our northern states and of the Laurentian peneplain of Canada. The lake basins of the Wisconsin drift are of several different classes. Many are shallow sags in the ground moraine. Still more numerous are the lakes set in hollows among the hills of the terminal moraines, such as the thousands of lakelets of eastern Massachusetts. Indeed, the terminal moraines of the Wisconsin drift may often be roughly traced on maps by means of belts of lakes and ponds. Some lakes are due to the blockade of ancient valleys by morainic debris, and this class includes many of the lakes of the Adirondacks, the mountain regions of New England, and the Laurentian area. Still other lakes rest in rock basins scooped out by glaciers. In many cases lakes are due to more than one cause, as where preglacial valleys have both been basined by the ice and blockaded by its moraines. The Finger Lakes of New York, for example, occupy such glacial troughs. Massive terminal moraines, which mark the farthest limits to which the Wisconsin ice advanced, have been traced from Cape Cod and the islands south of New England, across the Appalachians and the Mississippi Valley, through the Dakotas, and far to the north over the plains of British America. Where the ice halted for a time in its general retreat, it left recessional moraines, as this variety of the terminal moraine is called. The moraines of the Wisconsin drift lie upon the country like great festoons, each series of concentric loops marking the utmost advance of broad lobes of the ice margin and the various pauses in their recession. Behind the terminal moraines lie wide till plains, in places studded thickly with drumlins, or ridged with an occasional esker. Great outwash plains of sand and gravel lie in front of the moraine belts, and long valley trains of coarse gravels tell of the swift and powerful rivers of the time. The loess of the Mississippi Valley. A yellow earth, quite like the loess of China, is laid broadly as a surface deposit over the Mississippi Valley from eastern Nebraska to Ohio outside the boundaries of the Iowan and the Wisconsin Drift. Much of the loess was deposited in Iowan times. It is younger than the earlier drift sheets, for it overlays their weathered and eroded surfaces. It thickens to the Iowan drift border, but is not found upon that drift. It is older than the Wisconsin, for in many places it passes underneath the Wisconsin terminal moraines. In part the loess seems to have been washed from glacial waste and spread in sluggish glacial waters, and in part to have been distributed by the wind from plains of aggrading glacial streams. Fig 364. Bank of loess, Iowa. The effects of the ice invasions on rivers. The repeated ice invasions of the Pleistocene profoundly disarranged the drainage systems of our northern states. In some regions the ancient valleys were completely filled with drift. On the withdrawal of the ice the streams were compelled to find their way, as best they could, over a fresh land surface, where we now find them flowing on the drift in young, narrow channels. But hundreds of feet below the ground the well driller and the prospector for coal and oil discover deep, wide, buried valleys cut in rock, the channels of preglacial and interglacial streams. In places the ancient valleys were filled with drift to a depth of 100 feet, and sometimes even to a depth of 400 and 500 feet. In such valleys, rivers now flow high above their ancient beds of rock on floors of valley drift. Many of the valleys of our present rivers are but patchworks of preglacial, interglacial, and postglacial courses, Fig 366. Here the river winds along an ancient valley with gently sloping sides and a wide alluvial floor perhaps a mile or so in width, and there it enters a young, rock-walled gorge, whose rocky bed may be crossed by ledges over which the river plunges in waterfalls and rapids. Click on image to view large-sized Fig 365. Preglacial drainage, Upper Ohio Valley. After Chamberlain and Leverett, in such cases it is possible that the river was pushed to one side of its former valley by a lobe of ice, and compelled to cut a new channel in the adjacent uplands. A section of the valley may have been blockaded with morainic waste, and the lake formed behind the barrier may have found outlet over the country to one side of the ancient drift-filled valley. In some instances it would seem that during the waning of the ice sheets, glacial streams, while confined within walls of stagnant ice, cut down through the ice and incised their channels on the underlying country, in some cases being let down on old river courses, and in other cases excavating gorges in adjacent uplands. Fig 366. A patchwork valley. A and A, ancient courses still occupied by the river. B, postglacial gorge. C, ancient course now filled with drift Pleistocene lakes. Temporary lakes were formed wherever the ice front dammed the natural drainage of the region. Some, held in the minor valleys crossed by ice lobes, were small, and no doubt many were too short-lived to leave lasting records. Others, long held against the northward sloping country by the retreating ice edge, left in their beaches their clayey beds, and their outlet channels permanent evidences of their area and depth. Some of these glacial lakes are thus known to have been larger than any present lake. Lake Agassiz, named in honor of the author of the theory of continental glaciation, is supposed to have been held by the united front of the Keewatin and the Labrador ice fields as they finally retreated down the valley of the Red River of the North and the drainage basin of Lake Winnipeg. From first to last Lake Agassiz covered 110,000 square miles in Manitoba and the adjacent parts of Minnesota and North Dakota, an area larger than all the Great Lakes combined. It discharged its waters across the divide which held it on the south, and thus excavated the valley of the Minnesota River. The lake bed, a plain of till, was spread smooth and level as a floor with lacustrine silts. Since Lake Agassiz vanished with the melting back of the ice beyond the outlet by the Nelson River into Hudson Bay, there has gathered on its floor a deep humus, rich in the nitrogenous elements so needful for the growth of plants, and it is to the soil that the region owes its well-known fertility. The Great Lakes. The basins of the Great Lakes are broad preglacial river valleys, warped by movements of the crust still in progress, enlarged by the erosive action of lobes of the continental ice sheets, and blockaded by their drift. The complicated glacial and post-glacial history of the lakes is recorded in old strand lines which have been traced at various heights about them, showing their areas and the levels at which their waters stood at different times. With the retreat of the lobate Wisconsin ice sheet toward the north and east, the southern and western ends of the basins of the Great Lakes were uncovered first, and here, between the receding ice front and the slopes of land which faced it, lakes gathered which increased constantly in size. The lake which thus came to occupy the western end of the Lake Superior Basin discharged over the divide at Duluth down the St. Croix River, as an old outlet channel proves. That which held the southern end of the basin of Lake Michigan sent its overflow across the divide at Chicago via the Illinois River to the Mississippi. The lake which covered the lowlands about the western end of Lake Erie discharged its waters at Fort Wayne into the Wabash River. The ice still blocked the Mohawk and St. Lawrence valleys on the east, while on the west it had retreated far to the north. The lakes become confluent in wide expanses of water, whose depths and margins, as shown by their old lake beaches, varied at different times with the position of the confining ice and with warpings of the land. These vast water bodies, which at one or more periods were greater than all the Great Lakes combined, discharged at various times across the divide at Chicago, near Syracuse, New York, down the Mohawk Valley, and by a channel from Georgian Bay into the Ottawa River. Last of all, the present outlet by the St. Lawrence was established. The beaches of the glacial lakes just mentioned are now far from horizontal. That of the lake which occupied the Ontario Basin has an elevation of 362 feet above tide at the west and of 675 feet at the northeast, proving here a differential movement of the land since glacial times amounting to more than 300 feet. The beaches which mark the successive heights of these glacial lakes are not parallel, hence the warping began before the glacial epoch closed. We have already seen that the contaying of the region is still in progress, p. 198. The Champlain subsidence. As the glacial epoch approached its end, and the Labrador ice field melted back for the last time to near its source, the land on which the ice had lain in eastern North America was so depressed that the sea now spread far and wide up the St. Lawrence Valley. It joined with Lake Ontario, and extending down the Champlain and Hudson valleys, made an island of New England and the maritime provinces of Canada. The proofs of this subsidence are found in old sea beaches and sea-laid clays resting on Wisconsin till. At Montreal such terraces are found 620 feet above sea level, and along Lake Champlain where the skeleton of a whale was once found among them at from 500 to 400 feet. The heavy delta which the Mohawk River built at its mouth in this arm of the sea now stands something more than 300 feet above sea level. The clays of the Champlain subsidence pass under water near the mouth of the Hudson, and in northern New Jersey they occur 200 feet below tide. In these elevations we have measures of the warping of the region since glacial times. The western United States in glacial times. The western United States was not covered during the Pleistocene by any general ice sheet, but all the high ranges were capped with permanent snow and nourished valley glaciers, often many times the size of the existing glaciers of the Alps. In almost every valley of the Sierras and the Rockies the records of these vanished ice streams may be found in cirques, glacial troughs, rocks moutonnées, and morainic deposits. It was during the glacial epoch that Lakes Bonneville and Lahontan, p. 107, were established in the Great Basin, whose climate must then have been much more moist than now. Fig. 367. A valley in the driftless area. The driftless area In the upper Mississippi Valley there is an area of about 10,000 square miles in southwestern Wisconsin and the adjacent parts of Iowa and Minnesota, which escaped the ice invasions. The rocks are covered with residual clays, the product of long preglacial weathering. The region is an ancient peneplain, uplifted and dissected in late tertiary times, with mature valleys whose gentle gradients are unbroken by waterfalls and rapids. Thus the driftless area is in strong contrast with the immature drift topography about it, where lakes and waterfalls are common. It is a bit of preglacial landscape, showing the condition of the entire region before the glacial epoch. The driftless area lay to one side of the main track of both the Keewatin and the Labrador ice fields, and at the north it was protected by the uplands south of Lake Superior, which weakened and retarded the movement of the ice. South of the driftless area the Mississippi Valley was invaded at different times by ice sheets from the west, the Kansan and the Iowan, and again by the Illinoisan ice sheet from the east. Again and again the Mississippi River was pushed to one side or the other of its path. The ancient channel which it held along the Illinoisan ice front has been traced through southeastern Iowa for many miles. Fig. 368. Cross-section of a valley in eastern Iowa. A. Country rock. B. Kansan till. C. Loess. T. Terrace of reddish sands and decayed pebbles above reach of present stream. S. Stream. Fp. Floodplain of S. What is the age of rock-cut valley and of the alluvium which partially fills it, compared with that of the Kansan till? With that of the Loess? Give the complete history recorded in the section. Benefits of glaciation. Like the driftless area, the preglacial surface over which the ice advanced seems to have been well dissected after the late tertiary uplifts, and to have been carved in many places to steep valley slopes and rugged hills. The retreating ice sheets, which left smooth plains and gently rolling country over the wide belt where glacial deposition exceeded glacial erosion, have made travel and transportation easier than they otherwise would have been. The preglacial subsoils were residual clays and sands, composed of the insoluble elements of the country rock of the locality, with some minglings of its soluble parts still undissolved. The glacial subsoils are made of rocks of many kinds, still undecayed and largely ground to powder. They thus contain an inexhaustible store of the mineral foods of plants, and in a form made easily ready for plant use. On the preglacial hillsides the humus layer must have been comparatively thin, while the broad glacial plains have gathered deep black soils, rich in carbon and nitrogen taken from the atmosphere. To these soils and subsoils a large part of the wealth and prosperity of the glaciated regions of our country must be attributed. The ice invasions have also added very largely to the water power of the country. The rivers which in preglacial times were flowing over graded courses for the most part, were pushed from their old valleys and set to flow on higher levels, where they have developed waterfalls and rapids. This power will probably be fully utilized long before the coal beds of the country are exhausted, and will become one of the chief sources of the national wealth. The recent epoch. The deposits laid since glacial times graduate into those now forming along the ocean shores, on lake beds, and in river valleys. Slow and comparatively slight changes, such as the warpings of the region of the Great Lakes, have brought about the geographical conditions of the present. The physical history of the recent epoch needs here no special mention. The life of the Quaternary. During the entire Quaternary, invertebrates and plants suffered little change in species, so slowly are these ancient and comparatively simple organisms modified. The Mammalia, on the other hand, have changed much since the beginning of Quaternary time. The various species of the present have been evolved, and some lines have become extinct. These highly organized vertebrates are evidently less stable than our lower types of animals, and respond more rapidly to changes in the environment. Pleistocene mammals. In the Pleistocene the Mammalia reached their culmination both in size and in variety of forms, and were superior in both these respects to the mammals of today. In Pleistocene times in North America there were several species of bison, one whose wide-spreading horns were 10 feet from tip to tip, a gigantic moose elk, a giant rodent, castoroids, 5 feet long, several species of musk oxen, several species of horses more akin, however, to zebras than to the modern horse, a huge lion, several saber-toothed tigers, immense edentates of several genera, and largest of all the mastodon and mammoth. Fig 369. Megatherium. The largest of the edentates was the megatherium, a clumsy ground sloth bigger than a rhinoceros. The bones of the megatherium are extraordinarily massive, the thigh bone being thrice as thick as that of an elephant, and the animal seems to have been well able to get its living by overthrowing trees and stripping off their leaves. The glyptodon was a mailed edentate, 8 feet long, resembling the little armadillo. These edentates survived from tertiary times, and in the warmer stages of the Pleistocene ranged north as far as Ohio and Oregon. Fig 370. Glyptodon. The great proboscideans of the glacial epoch were about the size of modern elephants, and somewhat smaller than their ancestral species in the Pliocene. The mastodon ranged over all North America south of Hudson Bay, but had become extinct in the Old World at the end of the Tertiary. The elephants were represented by the mammoth, which roamed in immense herds from our middle states to Alaska, and from Arctic Asia to the Mediterranean and Atlantic. It is an oft-told story how about a century ago, near the Lena River in Siberia, there was found the body of a mammoth which had been safely preserved in ice for thousands of years, how the flesh was eaten by dogs and bears, and how the eyes and hoofs and portions of the hide were taken with the skeleton to St. Petersburg. Since then several other carcasses of the mammoth, similarly preserved in ice, have been found in the same region, one as recently as 1901. We know from these remains that the animal was clothed in a coat of long, coarse hair, with thick brown fur beneath. Fig 371. Skull of musk ox, from Pleistocene deposits, Iowa. The distribution of animals and plants. The distribution of species in the glacial epoch was far different from that of the present. In the glacial stages Arctic species ranged south into what are now temperate latitudes. The walrus throve along the shores of Virginia and the musk ox grazed in Iowa and Kentucky. In Europe the reindeer and Arctic fox reached the Pyrenees. During the Champlain Depression Arctic shells lived along the shore of the arm of the sea which covered the St. Lawrence Valley. In interglacial times of milder climate the Arctic fauna-flora retreated, and their places were taken by plants and animals from the south. Peccaries, now found in Texas, ranged into Michigan and New York, while great sloths from South America reached the Middle States. Interglacial beds at Toronto, Canada, contain remains of forests of maple, elm, and pawpaw, with mollusks now living in the Mississippi Basin. What changes in the forests of your region would be brought about, and in what way, if the climate should very gradually grow colder? What changes if it should grow warmer? On the Alps and the highest summits of the White Mountains of New England are found colonies of Arctic species of plants and insects. How did they come to be thus separated from their home beyond the Arctic Circle by 1,000 miles and more of temperate climate impossible to cross? Man, along with the remains of the characteristic animals of the time which are now extinct, there have been found in deposits of the glacial epoch in the Old World relics of Pleistocene man, his bones, and articles of his manufacture. In Europe, where they have best been studied, human relics occur chiefly in peat bogs, in loess, in caverns where man made his home, and in high river terraces sometimes 80 and 100 feet above the present flood plains of the streams. In order to understand the development of early man, we should know that prehistoric peoples are ranked according to the materials of which their tools were made and the skill shown in their manufacture. There are thus 4 well-marked stages of human culture preceding the written annals of history, 4. The Iron Stage. 3. The Bronze Stage. 2. The Neolithic, Recent Stone, Stage. 1. The Paleolithic, Ancient Stone, Stage. In the Neolithic stage the use of the metals had not yet been learned, but tools of stone were carefully shaped and polished. To this stage the North American Indian belonged at the time of the discovery of the continent. In the Paleolithic stage, stone implements were chipped to rude shapes and left unpolished. This, the lowest state of human culture, has been outgrown by nearly every savage tribe now on Earth. A still earlier stage may once have existed, when man had not learned so much as to shape his weapons to his needs, but used chance pebbles and rock splinters in their natural forms. Of such a stage, however, we have no evidence. Fig. 372. Paleolithic implement from Great Britain. Paleolithic man in Europe. It was to the Paleolithic stage that the earliest men belonged whose relics are found in Europe. They had learned to knock off two-edged flakes from flint pebbles, and to work them into simple weapons. The great discovery had been made that fire could be kindled and made use of, as the charcoal and the stones discolored by heat of their ancient hearths attest. Caves and shelters beneath overhanging cliffs were their homes or camping places. Paleolithic man was a savage of the lowest type, who lived by hunting the wild beasts of the time. Skeletons found in certain caves in Belgium and France represent perhaps the earliest race yet found in Europe. These short, broad-shouldered men, muscular, with bent knees and stooping gait, low-browed and small of brain, were of little intelligence and yet truly human. The remains of Pleistocene man are naturally found either in caverns, where they escaped destruction by the ice sheets, or in deposits outside the glaciated area. In both cases it is extremely difficult, or quite impossible, to assign the remains to definite glacial or interglacial times. Their relative age is best told by the fauna with which they are associated. Thus the oldest relics of man are found with the animals of the late Tertiary or early Quaternary, such as a species of hippopotamus and an elephant more ancient than the mammoth. Later in age are the remains found along with the mammoth, cave bear and cave hyena, and other animals of glacial time which are now extinct, while more recent still are those associated with the reindeer, which in the last ice invasion roamed widely with the mammoth over Central Europe. Fig. 373. Paleolithic sketch on ivory of the mammoth. The caves of southern France. These contain the fullest records of the race, much like the Eskimos in bodily frame, which lived in Western Europe at the time of the mammoth and the reindeer. The floors of these caves are covered with a layer of bone fragments, the remains of many meals, and here are found also various articles of handicraft. In this way we know that the savages who made these caves their homes fished with harpoons of bone, and hunted with spears and darts tipped with flint and horn. The larger bones are split for the extraction of the marrow. Among such fragments no split human bones are found. This people, therefore, were not cannibals. Bone needles imply the art of sewing, and therefore the use of clothing, made no doubt of skins, while various ornaments, such as necklaces of shells, show how ancient is the love of personal adornment. Pottery was not yet invented. There is no sign of agriculture. No animals had yet been domesticated, not even man's earliest friend, the dog. Certain implements, perhaps used as the insignia of office, suggest a rude tribal organization and the beginnings of the state. The remains of funeral feasts in front of caverns used as tombs point to a religion and the belief in a life beyond the grave. In the caverns of southern France are found also the beginnings of the arts of painting and of sculpture. With surprising skill these Paleolithic men sketched on bits of ivory the mammoth with his long hair and huge curved tusks, frescoed their cavern walls with pictures of the bison and other animals, and carved reindeer on their dagger heads. Fig. 374. Restoration of head of Pithecanthropus erectus early man on other continents. Paleolithic flints curiously like those of Western Europe are found also in many regions of the Old World in India, Egypt, and Asia Minor beneath the earliest vestiges of the civilization of those ancient seats, and sometimes associated with the fauna of the glacial epoch. In Java there were found in 1891, in strata early Quaternary or late Pliocene in age, parts of a skeleton of lower grade, if not of greater antiquity, than any human remains now known. Pithecanthropus erectus, as the creature has been named, walked erect, as its thigh bone shows, but the skull and teeth indicate a close affinity with the ape. In North America there have been reported many finds of human relics in valley trains, loess, old river gravels buried beneath lava flows, and other deposits of supposed glacial age, but in the opinion of some geologists sufficient proof of the existence of man in America in glacial times has not as yet been found. These finds in North America have been discredited for various reasons. Some were not made by scientific men accustomed to the closest scrutiny of every detail. Some were reported after a number of years, when the circumstances might not be accurately remembered, while in a number of instances it seems possible that the relics might have been worked into glacial deposits by natural causes from the surface. Man, we may believe, witnessed the great ice fields of Europe, if not of America, and perhaps appeared on Earth under the genial climate of preglacial times. Nothing has yet been found of the line of man's supposed descent from the primates of the early Tertiary, with the possible exception of the Java remains just mentioned. The structures of man's body show that he is not descended from any of the existing genera of apes. And although he may not have been exempt from the law of evolution that method of creation which has made all life on Earth akin yet his appearance was an event which in importance ranks with the advent of life upon the planet, and marks a new manifestation of creative energy upon a higher plane. There now appeared intelligence, reason, a moral nature, and a capacity for self-directed progress such as had never been before on Earth. The recent epoch. The glacial epoch ends with the melting of the ice sheets of North America and Europe, and the replacement of the Pleistocene mammalian fauna by present species. How gradually the one epoch shades into the other is seen in the fact that the glaciers which still linger in Norway and Alaska are the lineal descendants or the renewed appearances of the ice fields of glacial times. Our science cannot foretell whether all traces of the Great Ice Age are to disappear, and the Earth is to enjoy again the genial climate of the Tertiary, or whether the present is an interglacial epoch and the northern lands are comparatively soon again to be wrapped in ice. Neolithic man. The wild Paleolithic men vanished from Europe with the wild beasts which they hunted, and their place was taken by tribes, perhaps from Asia, of a higher culture. The remains of Neolithic man are found, much as are those of the North American Indians, upon or near the surface, in burial mounds, in shell heaps, the refuse heaps of their settlements, in peat bogs, caves, recent floodplain deposits, and in the beds of lakes near shore where they sometimes built their dwellings upon piles. The successive stages in European culture are well displayed in the peat bogs of Denmark. The lowest layers contain the polished stone implements of Neolithic man, along with remains of the Scotch fir. Above are oak trunks with implements of bronze, while the higher layers hold iron weapons and the remains of a beech forest. Neolithic man in Europe had learned to make pottery, to spin and weave linen, to hew timbers and build boats, and to grow wheat and barley. The dog, horse, ox, sheep, goat, and hog had been domesticated, and, as these species are not known to have existed before in Europe, it is a fair inference that they were brought by man from another continent of the Old World. Neolithic man knew nothing of the art of extracting the metals from their ores, nor had he a written language. The Neolithic stage of culture passes by insensible gradations into that of the Age of Bronze, and thus into the recent epoch. In the recent epoch the progress of man in language, in social organization, in the arts of life, in morals and religion, has left ample records which are for other sciences than ours to read. Here, therefore, geology gives place to archaeology, ology and history. Our brief study of the outlines of geology has given us, it is hoped, some great and lasting good. To conceive a past so different from the present has stimulated the imagination, and to follow the inferences by which the conclusions of our science have been reached has exercised one of the noblest faculties of the mind, the reason. We have learned to look on nature in new ways. Every landscape, every pebble now has a meaning and tells something of its origin and history, while plants and animals have a closer interest since we have traced the long lines of their descent. The narrow horizons of human life have been broken through, and we have caught glimpses of that immeasurable reach of time in which nebulae and suns and planets run their courses. Moreover, we have learned something of that orderly and world-embracing progress by which the once uninhabitable globe has come to be man's well-appointed home, and life appearing in the lowliest forms has steadily developed higher and still higher types. Seeing this process enter human history and lift our race continually to loftier levels, we find reason to believe that the upward movement of the geological past is the manifestation of the same wise power which makes for righteousness and good, and that this unceasing purpose will still lead on to nobler ends. Index A B C D E F G H I J K L M N O P Q R S T U V W Y Z A A, lava, 241, Acadian coal field 354, accretion hypothesis, 304, acidic rocks, 249, Adelsberg Grotto, 47, Adirondacks, 309, 316, Africa, 357, Agassiz, Lake, 67, 111, 435, Agates, 251, Alabama, 317, 360, Alaska, 85, 138, 140, 378, Aletsch Glacier, 121, Algae, 51, 52, Algonquian Era, 306, 310, Allegheny Mountains 90, 224, 326, 403, Alluvial cones, 98, Alluvium, 62, Alps, 118, 121, 141, 210, 211, 212, 223, 229, 349, 427, 443, Amazon River 175, Ammonites, 294, 367, 380, 382, Amphibians, 364, 383, Amphicean, 413, Amygdules, 250, Andes, 236, 279, Angle of Repose, 25, Antarctic continent, 294, Antecedent streams, 209, Antelope, 413, Anthracite, 281, Anticlinal folds, 203, 209, Ants, 20, Apennine Mountains, 399, Appalachia, 317, 351, 358, Appalachian Coal Field, 356, Appalachian Deformation, 358, Appalachian Mountains, 211, 214, 218, 292, Aquifer, 44, Aragonite, 296, Archaeology, Opteryx, 393, Archean Era, 305, Arenaceous rocks, 9, Argillaceous rocks, 9, Arizona, 32, 75, 145, 151, 154, 220, 229, 249, 257, 371, 390 Arkansas, 337, 356, 373 Arcos, 186, 282, 370 Artesian Wells, 44 Arthropods, 322 Artiodactyls, 411 Assiniboine, Mount, 34 Atlas Mountains, 399 Atmosphere, 304, 305 Atolls, 191, 193 Augite, 274 Austin, Texas, 71 Australia, 190, 357 Avalanches, 26 B Badlands, 397, 398 Baltic Sea, 170, 171, 199 Barite, 287 Barrier Reefs, 191, 192 Basal Conglomerate, 173, 184 Basalt, 249 Base Level, 80, 83 Basic Rocks, 249 Basin Deposits, 103 Bay Bars, 164 Beaches, 162, 164 Bears, 413 Bedding Plains, 5 Belemnites, 382 Belt Mountains, 309 Bergsgrund, 121, 135, 137 Bermudas, 148 Birds, 392 Bison, 413 Bitterroot Mountains, 272 Black Hills, 309, 371 Blastoids, 339 Blastosphere, 311 Block Mountains, 222, 226 Blowholes, 159 Blue Ridge, 309, 316 Bomb, Volcanic, 256 Bonneville, Lake, 107, 438 Bosses, 270 Boulders, Erratic, 420 of Weathering, 28 Brachiopods, 323, 333, 343, 364, 380 Brazil, 18, 236 Breccia, 218, 255, 264. British Columbia,